Question number 4 says the incomplete nuclear equation for one possible reaction that takes place in a nuclear reactor is shown. You can see, my dear students, that uranium-92 with 235, 1 neutron absorbs. It breaks into lanthanum, molybdenum, and 2 neutrons. Say the name given to this type of reaction. You know a large nucleus is splitting into 2 smaller nuclei. The splitting of a large nucleus into smaller nuclei is called nuclear fission. Complete the nuclear equation. Now they're asking you to complete the equation. In order to complete equation, I told you last time, you balance the nuclear numbers and proton numbers. If you talk about nuclear numbers, 235 plus 1, it should be same as 139 plus 95 plus 2 plus we don't know. You solve this equation and check what is the value of x. How much x comes? 0, yes? So 0 means up, whatever is the particle, its nuclear number will be 0. Up will be 0. If you go down, my dear students, down, this is 92, this is 0, should be 57 plus 42 plus 0 plus x. You solve, how much is this x? X comes -7. So -7 means there are 7 particles which have charge -1. So which particle has, you can either say beta minus or you can say electron. Both answers will be correct, my dear students. Equation we balanced. Now the next question is the mass defect of the reaction is 0.223. Calculate the energy in joules. So energy using Einstein's equation, you say E is equals to delta M C squared. This is mass defect, which is delta M. Delta M is 0.223 U. U means 1.66 into 10 power negative 19. Sorry, negative 27. That's the U. Into speed of light, C, 3.0 into 10 power 8 square. So you solve, substitute, you get the answer. Since given values are 3 significant, you will also give 3 significant figures. The next part, state 2 forms of energy which is released in this reaction. Certainly the products, they have motion. So motion means they have kinetic energy. Number 2, you know when beta negative is emitted, alongside beta negative, the antineutrinos are also emitted. Plus there are always gamma ray photons. Any of those 3 answers you can write. So you know that whenever beta is emitted, so there are what? It's beta negative or positive? Beta negative antineutrinos, yes? Gamma ray photons emitted, and there is kinetic energy of what? Products. Perfect, my dear. So these are the different forms which are released during nuclear reaction. Let's proceed to the next question. Explain what is meant by binding energy. Binding energy, last time we defined in a very good way, is the minimum amount of external energy needed to separate apart the nucleons to infinity. Minimum amount of energy needed to separate apart nucleons to infinity. Binding energy is the amount of energy needed to separate apart the nucleons to infinity. The next question is the following nuclear reaction takes place. You can see you have uranium 9235, 1 neutron is added, gives you cesium and rubidium plus Y neutrons. Determine the values of X and Y. You just need to balance. First you get X and then we get Y. So for X, my dear, you will say 92 plus 0, 55 plus X plus 0. Sorry? So X is equals to 37. You got X 37, my dear. Now Y. So Y is up. So if you go up, you will say 235 plus 1 is equals to 144 plus 90 plus 1Y. Solve it. 2. So answer is 2, my dear. Now the next question is state the name of this type of reaction. You already know a large nucleus is splitting to form the two smaller nuclei. So this reaction is called nuclear fission. A large nucleus is splitting into smaller nuclei. Now they say compare the binding energy per nucleon of uranium with the binding energy per nucleon of cesium. Dear students, you know cesium is a product. Products are always more stable. Yes, uranium is a parent. So actual uranium is unstable, right? And products are more stable. I think it's 5. Page number 19. So since, as I told you, the cesium is a product. The products are more stable. So more stable means what? It has greater binding energy per nucleon, yes? So they say compare the binding energy of nucleon of uranium. So uranium 235 has lower or less? Less is better. Binding energy per nucleon than cesium 144. If they ask you explain, because cesium is a product which is more stable. So more stable means it has more binding energy per nucleon. There is another reason, although it's not to be written, keep in your mind, these both nucleon numbers are after 56, yes? So the one which has a greater nucleon number, it has lower binding energy per nucleon, yeah? So if uranium, you look 235, it is at the end of the binding energy graph. So it is less stable. So less stable mean less binding energy per nucleon. Anyhow, they did not ask for reason. There might be more questions for asking reasons. So after that, my dear, yttrium 90 decays to zirconium 90, a stable isotope. Initial sample of pure yttrium is pure Initial sample is pure yttrium. So actually, whatever is the case, the Y is changing into zirconium. Z, I don't know the spellings, but it's fine. Yani. Y is changing. Zirconium is ZR, صح? If you know chemistry. So calculate the time in decays when the ratio of number of yttrium to the zirconium would be 2. Mean number of yttrium over number of zirconium is 2. 2 ratio, 2 mean 2 ratio 1. It means now if yttrium are 2, zirconium is 1. So initially, how many yttrium were there? 3. Why? Think, my dear students. Because look, everybody, the yttrium is giving you zirconium. Yes? So initially, we don't know how many were there, but right now these are 2. This is 1. So this one came from where? From one decay of yttrium. So if right now there are 2 yttrium, 1 zirconium. So 1 zirconium is as a result of decay of 1 yttrium. So now initial yttrium is 3. It's a good question. So what do you do, my dear students, in this question? What is the activity formula? A is equals to A naught e power negative lambda t, right? A now present. So present are 2 yttrium, right? Initial we made 3 yttrium. E power negative. Lambda is the decay constant. Yes? We don't have decay constant, but half-life we have. Sorry? ln2 over half-life. ln lambda is, my dear, log 2 over half-life. So it is going to be log 2. Half-life is what? Can I use days? I'm using days, so I will get days. Okay? Now, dear student, divide by 3. 2 divided by 3 is e power negative ln2 over 2.7 into t. Using the third law of logarithm, whatever is the power of the logarithm, you will bring it down. Yes? This power comes here. 2 by 3 negative ln 2 over 2.7 into, I didn't do the log. We were first supposed to take log. So it comes down after taking log. So it will be ln e. You all know ln e is 1. Please solve this equation. Time how much? 1.579 days. Now what unit you need? You also need days, so just write 1.6 days. My dear students, there was a trick to this question. Please make sure you review this. The trick was they gave you the ratio. They gave you the ratio. So if ratio was 2 ratio 1, so present amount of yttrium is 2, so zirconium is 1. So it means the total has to be 3, and total is called initial activity. So we got the answer 1.6. You can copy. If you have a question, you can absorb this information before I ask. We solve the next question. No question? Let's proceed. Question number 6. A very easy part. They're asking you the meaning of spontaneous decay. Decay has two natures, spontaneous and random. Spontaneous decay, I told you, the decay that is not affected by any external factors, external conditions like temperature, pressure, or presence of any other radioactive isotope. So decay uh, is not affected independent of, very good, by any external factor, external condition. Any word could be written. A random decay, each nucleus has equal chances or probability to decay. Yes? Equal probability to decay, hence impossible to what? Impossible to predict. Okay, these are the two natures of decay, and after this, strontium 90 is an unstable nuclide. Activity of the sample of 1.010 per minus 9 kilogram of strontium is this 5.2 mbq. M mean mega, BQ mean becquerel. It's a unit, yeah? Determine the decay constant lambda. So lambda, you know, log 2 over half-life, but half-life you don't have it. So idea will start from this point. What do you know, like how this mass can help you? It is strontium 90. So you need to know its number of nuclei. Number of nuclei. So first of all, ignore this. If I just want to talk about one nucleus, what is the mass of one nucleus? Huh? 90 U, right? Which is 90 times 1.66 10 power negative 27. Let's calculate what is the mass of one nucleus. This is the mass of one nucleus. Now we will find the number of nuclei. Yes, my dear students, total mass is 1.0 into 10 power minus 9 kilogram divided by mass of each nucleus is 1.494 into 10 power minus 25. So this is the total number of nuclei. We need n, the number of nuclei. 69 what? 10 power 15. Okay, since we don't have half-life, so we need to look for another formula of lambda. So what is the activity formula you learned? A was equals to lambda n. Okay, do we have activity? Yes. Do you have n? Yes, we do. You have n. You have activity. Can we find lambda now? So lambda will be activity 5.2 mega. Mega means 10 power 6 over 6.693 10 power 15. It's a good question. Calculated. Intermediate answers, please don't round off. Okay. Final, we will round.
7.76
minus 10. So 7.8 into 10 power negative 10 per second. Dear students, we could find lambda if you had half-life. We didn't have. We can also find the lambda using A is equals to lambda n. So A is activity we have. So number of nuclei we find using what? The total mass. You understand? Any question, my dear students? It's a good question. It's a very indirect question. You should be able to solve. Let's read the next part. The activity of the sample after time one half-life. Yani after one half-life. Yani it should be 50%. But it is found to be greater. Last time when we closed the topic, what did I tell you? That measured count could be different than the true count. Now we expected that the half of 5.2, it should be what? 2.6. But they are saying now it is greater. Last time I wrote general point for you, like maybe due to background, it is greater. Yes? Maybe the decay product is also radioactive. Both of these, they talk about this. So they say it is found to be greater. So what is the decay product? So you can just say the product or the daughter nuclei. Okay? So you can say decay product. Last time I told you the word, you can also say what? Daughter nuclei. Daughter nuclei are stable, yes? Or not stable, also unstable. Presence of background radiation is also one of the reasons causing to be greater. Okay, dear students? Hi, Muhammad, should I bring your book to school tomorrow? Or no need? Question number 7, my dear students. Polonium 211 decays by alpha emission to give you a stable. Now they already told you it is stable. So in such case, you will have to look for a different option. Polonium gives you lead and alpha. First of all, start with alpha. You all know alpha is 4, 2. Once you balanced alpha, you can balance the lead. So 211 minus 4 is 207. Similarly, 84 minus 2 will give you 82 is the lead, my dear students. So alpha, 4, 2, the rest we balanced. Any question? The variation with the time t of the number of unstable nuclei n, okay, n when you read, it is a multiple and it is 10 to the power 12 in the values. It is for polonium 211. Polonium means the parent element, parent nucleus, okay? So at time 0, the sample contains only polonium, which is 24 into 10 power 12, that is the initial value. Use the figure to determine decay lambda. Now lambda is determined by two equations. Either lambda is log 2 over half-life, or lambda is equals to A over N. N we have, activity we don't have. ln2, half-life, yes, we have. So half-life means the mean time taken for any radioactive sample to decay to half of its original value. Mean time taken for half of the elements to decay. So if total was initial 12, so half will, 24, the half will be 12, right? Good. Okay, dear students, what is this? The half-life? 4. This is 5. So this is 0.52 seconds. So your first step is to write half-life is 0.52 seconds. Then lambda is equals to logarithm of 2 over half-life seconds. So calculate this value, my dear students. 1.333. So 1.3 s minus 1. Because you use second, so per second. Days, per days. Good? Makes sense, my dear students? Now you have lambda and you want to calculate activity. Activity symbol is what? A. You have both. Write the other equation. A is equals to lambda n. Lambda you found 1.333, yeah? They say use the answer. Use the answer. N is the 24 10 power 12. Calculate, my dear students. 3.1 10 power 13 becquerels. On the figure, sketch to show variation with T, the number of lead nuclei. Lead is now daughter. Lead is what? Either we say daughter or we say decay product. Last lesson, when I ended my lesson explanation, I told you these decay curves should be symmetric about 50% of n. 50% of n is this. So your curve should be symmetric about this one. Yes? Yes or no? So my dear students, you can write some more points after that. Like when first is 24, the other will be 0, yes? Half, half. Okay? Yes or no? Their sum should be what? 24. You can choose any number, but the sum should be 24. Like for example, how much is this number? The final. It is 5 point. No. 5.2. So 24 minus 5.2, how much? 18.8. 18.8. 18. 2 boxes. If you want any more point, you can take. No problem. Uh, I can draw as many as I want. Okay, so their sum should be same. Yes, my dear.
One box is here from the box.
Where? No, it's correct. Yeah, Habibi. If down is 5.2, I'm counting this way. That should also be the same. Have you noticed? I'm doing the cheating. I just told you something else and doing something else. All are good except the last point of my graph. Why can't I select it? I was just impressed. The Kharban. I will do again. I know what to do. Bad. Maybe that. Okay. This is for the decay product, my dear students. Make sense? Yes. They should be symmetric about the 50%. Each decay releases an alpha particle with energy 6,900 kilo electron volt. Electron volt, you know, each electron volt is 1.6 into 10 power negative 19 joules. Calculate in joules the total amount of energy given to alpha particles that are between 3 and 0.9. So let's go. 3 seconds was they said, yeah? And 0 point? Oh. We need to know how many nuclei decayed, because each nucleus gives you 1 alpha. So it is 6, 7, 7.2, and 12. Yes, my dear student? No. 16, 10 power 12. So for this time, from 16 till 7.2, we need to know how many are emitted. How many are emitted? You can subtract them, my dear. Yes? So number of alpha released, because each nucleus releases 1. So 16 into 10 power 12 minus 7.2 into 10 power 12. 16, 8, 8.2, 8.8, right? This many alpha particles have been emitted. Yes? So what is the total energy now? Multiply them. 8.8 into 10 power 12 alpha. Each alpha is 6,900. Now look, kilo electron volt. 10 power 3 is for kilo. 1.6 into 10 power negative 19 is from electron volt to joules. For kilo, I did 10 power 3. Electron volt to joule, 10 power, 1.6 into 10 power negative 19. Calculate. Ten power. Nothing? Huh? 9.7 joules. Fair enough? Next question. You have a part, they ask you, suggest why the total amount of energy released by decay process between the time this and this is greater than what you calculated. Like the total energy released by decay process is more. Same as your last time you did. So some energy is released in the form of, this is for alpha. So kinetic energy of other products are what? Polonium. No, not polonium. Lead. Gamma ray photons also. So you will say there is kinetic energy of lead, emission of what? Gamma ray photon. Can I here say those neutrino, antineutrinos? Why no? Because those are for betas. If there is a beta emission, beta negative, we say antineutrino emissions also is accepted. If we say beta positive, we say neutrino emission. So this is the two answers are possible. You can write one of them, my dear students. Make sense? Yes? Question number 8. It says the polonium is unstable and undergoes alpha decay. So complete, it's quite similar to the previous one. So alpha, you all know, my dear students, it is 4, 2. Alpha is 4, 2. So now here you subtract 4, it will be 230. 4 subtract 2, 92. The power source in a space probe contains 0.874 of plutonium. Each nucleus gives you this energy. Half-life is this. Calculate the initial number. Again, the same concept, 2 questions before we did. We will find the mass of one nucleus or atom. They use the word nucleus or atom? Nucleus. Find the mass of one nucleus as you did before. Then divide the given mass by the mass of one nucleus. You will get the total number. We did it a while ago. So one nucleus mass. How many? They ask you for plutonium. 238 U. 238 times 1.66 times 10 power negative 27 kilograms. Okay? And directly write the number of atoms will be the given mass, how much? 0.874 divided by 238 into 1.66, 10 power negative 27. You know what did we do over here? We divided the total mass by mass of each nucleus. You get the number of nuclei present initially. Two 2.29 10 power 2.21 10 power 2.2 into 10 power 25. Since your given figures are all 3 significant figures, all the given digits values are 3 significant figures. So this should be kept 3. If you will round to 2, you will lose the mark. Why? You can see all the data values, 3 significant, 3 significant, 3 significant. So your answer should also be 3. 2 you will not write in this case. My next question is determine the initial activity of the source. Activity. So to find activity, we need to have lambda. Yeah? Activity formula, you know lambda n, right? But lambda is equals to log 2 over half-life. You can put the values, my dear students, and get the answer. Half-life how much? Years. If you use years, your answer will be per years. Yes, but I prefer it's sorry, it's not the decay lambda. Actually, we need activity. Activity unit is becquerel. Yeah. So becquerel needs per second. Becquerel needs per. So lambda, when you say ln2 over 87 years. So 87.7 years, you need to years into days, 365, days into hours, 24, hours into second, 3600. What did we do? We changed years into days into hours into seconds. Why did I change the unit, students? You should all know, because the unit of activity is becquerels. It has to be assuming that the lambda is per second times n. So n was 2.2 10 power 24. We first used lambda is equals to ln2 over half-life. We used first. Calculate, my dear students. Again, I kept three significant figures because the question value was three significant figures. Using the answer in B2 means activity. Determine initial power output of the source due to decay. Power, the power is what? Energy multiplied by time. Energy divided by time, sorry. Energy over time. Time we don't have. But time, like if it's actually joule per second. The power, when you say watt, is what? Joule per second. So can we do like energy times something which is per second? Make sense or no? Understanding or not? Now energy, we know from the source 5.59 mega electron volt. 5.59 mega electron volt. What does that mean? It is for one nucleus. Then you multiply by total number of nuclei, and then per second mean lambda. Per second mean, or okay, let's keep it like this. Energy times number of nucleus times lambda. Now, how can I use the answer? Girls and boys, look. Can I say E? What is N times lambda? A. So energy times activity is the power. I just proved for you. Yes? So just substitute, you get the answer. Did you understand how I related? What is joules per second? Joule is the energy. Energy of all of them is E times N. Lambda is per second. So N times lambda is activity. So just multiply energy. How much energy, my dear? 5.959 mega electron volt. So 5.59 mega mean 10 power 6. Electron mean 1.6 into 10 power negative 19. And the answer which we got, I don't have enough place. I will just, you substitute please. I will just move it a little bit like that. 5.54 10 power 14. Shoe 400. $495 watt. Make sense, students? Interesting? It's good. Nuclear physics is more interesting. It's the alternating current. It's capacitors. This is more variety of the concepts, you know. The space probe will continue to function until the power output of plutonium decreases to 65.3%. Decreases to, it's easy, means if maximum power is 100, yes? So new power is 65.3. Does it make sense? Yes. Now we already wrote, go up. The power is proportional to activity. Power is, look here, proportional to, so you can use the same relationship as you used to do for activity. So right here, since power is proportional to activity, so P will be P naught e power negative lambda t, right? Substitute the values, but this time they need in years. So I suggest you to keep lambda in years. So power 65.3 100 e power negative log 2 over how many years? 87.7. Please keep years because the answer is in years. Into t. Okay, so first you divide by 100 to the other side. Zero 0.653 e power negative ln 2 over 87.70 log. So log of 0.653, it will be negative log 2 over 87.7 into t. Rearrange and get the answer. 53.9 years. So space probe will function using how much mass? Nice. Yani, just less than 1 kilogram of this fuel. The space probe can function for 60 years. Okay. An alternative power source uses energy generated from radioactive decay of plutonium. What was the previous one? Previous one was plutonium. Yes? Now they are using polonium. This isotope's half-life is 0.378 years. What was the previous half-life? Do you know 87 years means what? Like it decays very slowly. Half-life of 0.378 years mean what? It decays very fast, quickly. Okay. The mass of the isotope needed for same is 3 gram. For same initial output. So previously we needed almost 800 grams for the space probe, right? But the half-life was long. This one, half-life is short, but the mass is just needed 3.37 grams. Yeah, very less mass is needed. Very less mass is needed. Yes, but half-life is very short, which means it will decay fast, so it will not continue for long time. So ideally, space probe, the best thing about this is the mass is very less. But the bad thing about this is short half-life will cause the decay to be too fast. Too fast decay rate means it will not last for long. So one advantage, one disadvantage, both we discussed. Less mass. So mass is much less. Yes. So less mass. Now you want to launch a heavy probe. You want to launch a light probe. Which one is good to launch? Light. So less mass, so very less energy will be needed to launch the probe. It's advantage. The disadvantage, you can say the half-life is too short. Short half-life means it will decay quicker and provide power for less time, or will not provide power for long time. We compare, my dear. Make sense? Next question. That was February 23, February 24. With this, all the February questions from 16 to 24. 9 years done. Yeah, each year is one, so ninth question. Question number 9 says, state what is meant by binding energy. We defined today at the beginning of lesson the minimum amount of external energy needed to separate apart nucleons to infinity. Minimum amount of external energy needed to separate apart the nucleons to infinity. Yes or no? The nucleus of uranium-235 absorbs a neutron. It becomes unstable. It then undergoes fission. One possible fission is this one. Determine the number of neutrons that are produced. So first of all, before you determine, write neutrons X, because neutron is 1, 0. Yes or no? And okay, so we need to know comparison method. The left side is 235 plus 1 equals to 142 plus 90. Yes? Sorry? Oh, yeah, sorry. 235 plus 1 plus x neutrons. Yes? Just solve. This will be the answer. Because x times 1 is x. 4. So 4 neutrons are emitted. Data shows binding energies per nucleon. So please make sure these all are for one nucleus, one nucleus, one nucleus. Why? Because they said it is per nucleon. Yani for each nucleon, this is the energy. Not nucleus, nucleon. So calculate the energy released in mega electron volt from the fission. Okay, go. So energy before reaction, do separate. Then energy after reaction, you do separate. Okay. Before, after. I need to look. How many uraniums are there in the question? Huh? 235 nucleons. How many? 235. So before 235 times 7.59. After we have xenon is 142, strontium is 90. 142, 8.37, 90, 8.72. So after decay, the energy. 142 times 8.37 and 90 times 8.72. 3, 4. So the energy released, subtract them, 1973.34 minus 178365. Sorry? 189.9. Now, certainly, I need to round it to 2 or 3, it's the same answer, 190. Yes? Whether you write 2 significant or you write 3, it has to be 190. There is no other option. Make sense? What? The isotope of xenon 142 is unstable. Yes? Reason, you already know. The reason of instability, when we studied isotopes, I say number of neutrons. Some people, they say nucleon number, but it's actually the ratio. It is what? Neutron to proton ratio. Higher the neutron to proton ratio, more the instability. Keep in your mind. When I taught you the isotopes, I told you those isotopes which have higher neutrons, they are more unstable, radioactive. So reason is the ratio of neutron to proton. So you can say greater number of neutron or higher neutron to proton ratio, both answers will be correct. Or neutron to proton ratio, just keep in your mind, if it is high, more unstable, more radioactive. Low, less unstable, yani stable. Xenon 142 decays into cesium 142. A sample initially contains only xenon. After time t 6 seconds, the ratio is 31. The ratio is 31. 31 means 31 ratio 1, my dear students. Yes or no? So calculate the half-life of xenon. Now, my dear students, so what does that mean? The ratio decayed to undecayed. Decayed to undecayed. Decayed mean that are gone. Undecayed mean which are still present. Okay. So if, yani, I just want to understand if initial was and not, yes? So undecayed, yani remaining, we say N, yes? So how many are decayed then? N naught minus N. Substitute. So decayed, yani N naught minus N. Yes? Over undecayed, yani remaining N is equals to 31. First of all, solve this equation. I mean, rearrange. Decayed. And n naught minus n is 31n. Yes? So n naught is 32n. Yes? Okay. So that's it. Now, my dear, in order to find half-life, the activity role is the n is equals to n naught e power lambda t. N is what? We don't know. N naught is what? 32n. By the way, why did I do this much hard work? 31 over 1. So it means total is 32. Easy. Can we do this? Yeah, that's more easier. No need to do all that hard work. So 31 over 1. Yes, so it means total is 32. So you know A is equals to A naught e power negative lambda t. So A naught yani undecayed 1, yes? Initial is 32. E power negative. Can we first find lambda? Time how much? 6 seconds. So, dear students, 1 over 32 e power minus 6 lambda. Take log on both sides. So log 1 over 32 is negative 6 lambda. Give me lambda. Log 1 over 32 divided by negative 6. Sorry?
2.5776.
So half-life, you know, lambda is log 2 over half-life. So half-life is log 2 over lambda, log 2 over 0.5776. Yalla habibi. A good question. This was March 24 question. With this, all the 9 years of March, have you noticed this topic is a certain question? Yeah. Sometimes when I was compiling this book, I realized there are 3 to 4 years when this didn't come, or 3 to 4 variants. Even recent May, June 23 or 24, some variants they don't have, but it's a good topic. Yani. So there are basic 3 equations which we frequently used. One is the activity equation, exponential. Other is the lambda equation. And one activity is non-exponential. Apart from that, Einstein's equation. So these 4 equations most commonly used. Let's continue to solve. After March, we start with June's. I actually added all the years for you. So June 2003. Question says, first of all, that you have strontium 90, which decays to give you beta negative, and 0.55 mega electron volt with yttrium. Decay constant. You all know decay constant symbol is lambda, right? Per year they gave you. Suggest with a reason which nucleus has greater binding energy. There are like many answers to this question. Binding energy, my dear, you know, just look at the nucleon number, yeah? Nucleon number, if they are after 56, yes? This always helps me if I forget the things. Peak is at, place them, 38, 39. Sorry, 90 Oh, both are 90. This is the problem. This will not help. So let's go to the other concept. The other concept is the products are more stable. Products are more stable. And more stable means what? Greater binding energy. And we have one more thing. Today I told you neutron to proton ratio. Neutron to, you can check that one. If you check the neutron to proton ratio, the strontium has more neutron to proton ratio. Yes? So it is unstable. So yttrium is stable. The other criteria, which I already told you last time, the products are stable. So stable means more binding energy. Yes or no? So greater binding energy is yttrium. Spellings. More stable what? Also the energy is released. You can also give a reference to due to release of energy. When energy is already released, you became stable. A nuclear number didn't help me, but neutron number can help you. Actually, in my notes, I talked about neutron number. The one which has higher neutron number is unstable. The one which has less neutron number, it is stable. So I told you, you can mention it has fewer neutrons, yttrium, so it is stable. Stable means more binding energy. Make sense? Sure. What is meant by decay? Finally, this definition came. So decay constant lambda. Sorry? Probability of decay of any individual nucleus per unit time. And individual or a nucleus, you can say, per unit all right. At the time of purchase, strontium 90 source activity is this becquerels. Calculate for this sample initial number of atoms. Easy. Number of atoms and activity are related with A is equals to lambda n. So do we have lambda? Yeah. Becquerel assumes seconds, not per years. So this is the problem. The conversion is important. Yeah. Becquerel involves the per second, not per year. So that conversion will be a bit problem for you. Anyhow, lambda is, I mean, you want what? N. It is A over lambda. A is 3.87, 10 power 6. Now, here is the issue. It is 0.025 per year. It is per year. If year to second, we keep multiplying. Yes? But per year to per second, you keep dividing. So you will not multiply, you will divide by 365, 24, 3,600. Please keep in your mind, if you go from year to second, then you multiply by 365 and this. But you want to go from per year to per second for the sake of becquerel. It's a good to think about this conversion. يلا. 4.667. So 6, 7, 10 power. Now 15.
Sir, could you explain the conversion thing again? From year to second per second?
I will explain, my dear, but can you tell me how you use year to second? Yani, can you help me? First, you tell me, then I will tell you.
365 times
Times what?
24,
365, then 24, then what?
3600.
Very good. Excellent. So this is year to second. But if you want from per year to per second, per mean divide. So instead of multiply, you will make it divide.
Okay, okay.
Make sense?
Yeah.
Thank you. Initial mass. Now the same way. We had two questions like this before. This is the third one. Initial mass. I will first find for one nucleus. Yeah? One nucleus, M1 I say, yeah? Now, strontium, right? 90. Calculate this, my dear. Now, minus kilogram. Let's multiply then. Ten power. So, dear students, this concept of mass of one nucleus is tested in 3 questions so far. Have you noticed? What is not tested yet? Fusion, binding, calculating binding energy per nucleon, of the sample 5 years after it is purchased, then ratio A over A naught. Easy, my dear. Activity formula you already know. They say this is the ratio A over A naught. You know A is equals to A naught e power negative lambda t. This is so easy. So you want A over A naught. Yes? It is e power negative lambda t. Just substitute. Now, since time is years, you can use the lambda per years. So which was 0.0? The lambda, here you go, 0.025 per year. We don't need conversion. Why we don't need conversion? Because the time is already 5. Just give me the answer and write it. 90 what? E power 9 or 8? 882. 0.8. Next question, my dear students. Actually, this is the good graph. Similar, nuclear number, binding energy per nucleon. Mark letter S where the nucleus has greater stability. The peak. The peak. How exactly I identify the peak? Greater stability means maximum binding energy. You know, I think this will be iron, yani, maybe, yani, if I'm not wrong. Okay. One possible reaction is uranium gives you uranium with a neutron gives you barium, krypton, and 2 neutrons. So label U is uranium, label Kr is krypton. On figure 8.1. So we need to look where will be 90 and where will be 235. Yes? So 235 uranium is at the end. Can we label somewhere here? U. And 90 for Kr. Kr is 90. They need Kr and uranium. So 90 will be somewhere here. Yes, students? Make sense or no?
Yeah, it'll be between them.
Okay. So my dear students, binding energies. My dear students, again they are saying these are binding energies per nucleon. Yani, not nucleus, nucleon. So it is for one nucleon. So if you want for uranium, you will multiply by 235. For barium, 144. Hey, what are you doing? Why are you scaring me? And for krypton, you multiply by 9. Okay, dear students. Now, this data is actually given in the previous page. So use the energy release in this fish reaction. Use your answer to 3 significant figures. So you already know. Multiply. Can we do together now, Alatul? Yes or no? So 90 times 1.3864 10 power negative 12. Then out barium 144 1.3341 10 power negative 12 like this. Yes, minus 235 1.2191 10 power negative 12. 3 significant figures, please.
3.04 into 10 power negative 12.
Mass equivalent to this energy. Yes, mass energy formula. So M will be E over C square. It will be something into 10 power negative something. Because I know up is negative 11. The down is negative 16. So 11 and 16, 27. Time, it's with something 10 power negative 27 or negative 28.
28.
Told you. Told you. Told you. What's the answer?
3.37 multiplied into the power minus.
Why neutrons were not included? It doesn't require a binding energy, yes? It's a single particle. Yes or no? They don't have binding energy. My dear students, binding energy is for a nucleus. Alpha has binding energy. Question number 12, my dear students. An isotope of manganese 56 decays and undergoes beta particle emission to form the stable iron 56. Okay. I have a question. Even today I was discussing in my school also. Shahza, now in this case, if you look, manganese is also 56. Iron is also 56. How will you decide which one is more stable? Neutron to proton ratio. So if nuclear numbers are same for two different isotopes, then you look for neutron to proton ratio. Wa alaikum assalam wa rahmatullah. So anyhow, that was just a question. Half-life is 2.5 hours. Initially time is T. The sample of the manganese is 56. Is 1.4. So this is the initial amount. You can say A naught. Instead of A naught, you can say M naught. Okay. So complete the graph for 11 hours. So 11 hours and keep going for half-lives until you reach 11. So initial amount is 1.4. Okay, so here is 1.4, dear students. So if you do 0 0.2, 4, 6, 8, 12, 14, 16, 1, 2, 0 0.4, 0 0.6, 0 0.8, 1.0, 1.2, sorry, 00, right? What is correct? Okay, and it is in micrograms. The y-axis, you can say micrograms. Scale is ready. X-axis is already calibrated. Shaka, my dear, especially you make sure the gap is uniform. Yani, the scale spacing should be uniform. So initial is, as you can say, 1.4. Now when the half-life is 2.6, so it will be 0.7. Now where do you think is 2.6? Somewhere here? Yes? 0.7. 2.6 and 2.6, 5.2. Here is 5. So 5.2 will be 3.5, right? And 2.6 times 3, how much? Sorry? 7.8. Almost here, yes? And half of 0.35? 175. Plus 2.6 again? 10.4. And then you need till 1? Till 11, okay. So you make a smooth curve, dear students. This is how it should look like. So each time you kept doing half, half, half. You can use a ruler. Please make sure you use pencil in the graphs, okay? Okay. For the sample of manganese, determine the initial number of atoms. Number of atoms, I told you it is N. And initial is called N naught. So mass you will compare with the general way last time you learned. First go for one atom. 1, Atom. One atom mass, I'm using convention as M1. You remember last time? 56U. So 56 U mean 1.66 into 10 power negative 27 kilograms. Yes. So you want number of atoms? The total mass, how much they gave you initial? 1.4 micro. Oh, look, 1.4 micro mean 10 power minus 6. Gram to kilogram mean 10 power minus 3 kilogram. The initial mass. Make sense, students? This is the total mass divided by the number of mass of one atom. 56, 1.66. Last time I also told you whenever you want to relate the number of atoms with mass, you first need to find mass of one atom or one nucleus. We found, then we divide total by the one. You will get the answer, which is
1.6.
1.6 into 10 power 16, my dear students. Initial activity. Now, activity formula, you know, A is equals to lambda N. Is this the formula? But we don't have lambda. So lambda is ln 2 over half-life. So ln 2 half-life. Now half-life, becquerel, last time I told you, you should use per seconds. So the half-life is 2.6 hours. 2.6 hours mean times 3,600. And then you multiply by 1.6 10 power 16. Calculate. You are rounding off or
1.19.
okay. 1.2 into 10 power 12 becquerels. Make sense, students? Okay. Determine the time at which the ratio. This is the third question of its nature. Iron, manganese. Actually, it was like this. The manganese was giving you iron. If you read the question back. So if manganese is giving you iron, do you want the ratio? If they say it is what? 9. Can I say 9:1? Wa alaikum salam. Can I say 9:1, my dear student? So what do you mean by 9:1? So 9:1, when you write the activity formula, how do you write? A is equals to A naught e power negative lambda t, right? Or not right? My dear students, now 9:1 mean what? The iron are 9. So remaining manganese is 1. So initial manganese were 9 plus 1, 10. See, this is the iron, mean new formed are 9. Yani decayed. So undecayed is 1 out of 10. Making sense or not? Now you need hours. So you will use the lambda in hours. So lambda is ln 2 over 2 point into t. Those students who directly can do, I allow you. Others, look here. 1 divided by 10 e power minus, can you give me ln 2 over 2.6? T. So take ln. So it is ln 10. Sorry. Negative 2.666T. You can get the answer. 8 point. 8.6 hours it will take for ratio to be 9. Next question, my dear students. Define the decay constant. Decay constant is lambda. You should know how do we define lambda. Can anyone define? Probability of decay of a nucleus or any individual nucleus per unit time. The strontium-90 is a radioactive isotope. It is having a half-life of 28.0 years. Make sure your final answers, those who do calculations, should be 3 significant figures in this whole question. Strontium-90 has a density of 2.54 gram per centimeter cube. In case if you want to make conversions, each gram per centimeter cube is 1000 kilogram per meter cube. You learned in AS. A sample of strontium has an activity is this becquerel. So the data is in front of you. Half-life, you know. Activity, you know. Density. Let's see how we're going to use it. Decay constant. Decay constant is very easy. Just look at the unit, what unit you want per second. So half-life should be also in seconds. Decay constant equation, you all know lambda is equals to log 2 over half-life. Right, students? Log 2 over half-life is 28 years. So what do you do? 28 times 365 times 24 times 3600. 7.85 into 10 power negative 10. Mass of strontium in the sample. Now, my dear students, I told you already that whenever you want to relate the mass, you always start with mass of one nucleus, one atom. They are using the word nuclei or atom. Doesn't matter. Mass of one atom. M1. How do we get? 90 U. Can I keep 90 U and in divisions? Fine. Okay. Now the problem is the mass. For mass, we need number of atoms in the sample. Number of atoms in the sample formula, my dear. N is equals to A was lambda N. A was, so it will be A was lambda N. So N will be A over lambda. Now units of the matching. So A is a 6.4 10 power 9. A they gave you here, the activity. And lambda you found. 6.4 10 power 9. Lambda 7.85 10 power minus 10. So mass of one atom, you know. So total mass will be what? $90 U. times 8.15 10 power 18. Previous questions we used to have mass and find n or the lambda. Now it is opposite. They need grams. So that's kilogram. 1.10 power negative kilograms. You want grams, so multiply by 1000 to change into grams. Give me now new answer. It will be -3, right? Please always watch out the units they need. So in this case, they ask you in grams, but because the one which we are using, the mass of one atom, it is in kilograms. So we multiply by 1000 to change kilograms into grams. Next question. Volume, density now. So we don't need to make any conversion. You already know, my dear students, that density is equals to mass over volume. So volume is mass. You have in grams 1.22 10 power -3 over density is given as, here is the density. You can see 2.54 10 power 2.54 gram per centimeter cube. Again, give me 3 significant figures, the answer to this question. -4. Think about this volume, my dear. Think. How much is this volume? 1 centimeter cube is like this big stack. Yani 1 centimeter length, 1 width, 1 height, right? How much is this? Almost 10 power -4, yani 10,000. So 4 parts out of 10,000 of a centimeter cube. How much is this volume, my dear? A very small volume, a tiny volume. If you make 10,000 parts of a centimeter cube, so these are only 5 parts, almost, right? Yes or no? So by reference to this number, means this small volume, why does suggest why dust that has been contaminated with strontium presents a serious health hazard? Look, this small volume, look at the activity. 6 into 10 power 9 becquerels. Yani, this small volume, how much radiation is emitted per second? Becquerel mean radiations per second, the activity. How much? 6.4 into 10 power 9. Yani 6 billion radiations per second emitted by this volume. Is it safe? Dust is contaminated with the sample of strontium. So why it is very dangerous? So since 4.8 into 10 power -4 centimeter cube is very small volume and has very high activity. Very high activity. So the dust can be highly radioactive. Extremely radioactive, causing health issues, yes? use the same word, hazard. Activity question, my dear students, please open. A sample of radioactive isotope contains n nuclei at time t. And when delta t time passes, they are n minus delta n. N minus delta n. Mean delta n has been gone, emitted, decayed. So remaining is n minus delta n. They want the mean activity. So activity formula is what? Activity. The number of nuclei decayed per unit time. How many are decayed? Delta n. Time passed how much? Delta t. My dear, these are remaining. These are remaining. So how many decayed? Delta n are decayed. So activity is what? Rate of decay of nucleus, not probability. Probability is decay constant. Here is the probability. So you divide by n. Divide by n. So delta n over n delta t. So probability mean you divide by n. No, probability, no t. I thought it's just probability of decay. Probability of decay per unit time is decay constant. The lambda. They didn't ask you lambda. Mag. Probability per unit time is lambda, which is called decay constant. That's it. Cobalt 60 source having half-life 5.27 years is calibrated and found to have an activity. This one. Uncertainty in calibration is plus minus 2%. Okay. The length of the time in days after the calibration has been made for the activity, this maximum possible error is this. Half-life you have, activity you have, you want the time, the equations you know. So first of all, can we find the decay constant? Aratul do. A is equals to A naught e power negative lambda t. Yes or no? So uncertainty is 2% in calibration. Maximum possible error of 10%. Listen, so you want the time. .5 into 10 per 5 becquerel. And if you compare with 100, so uncertainty in calibration is 2%. And then to have a maximum possible error of 10%. Dear students, your error is whatever. Whatever is the error. There could be minus 2% due to calibration or plus 2% due to calibration. Yes? Understanding or not? Now they say the maximum possible error is what? 10. So maximum mean including the 2% of the calibration. Understanding or not? Again, look. The maximum possible is maximum mean by adding the uncertainty. By adding the uncertainty. Yani it's just like if you have the maximum is 10, uncertainty is 2. So it means mean will be 8. So it means minimum will be 6. So this is your variation in the calibration errors. Understanding or not? This is your variation in the calibration error. See how I am relating it. First, I'm relating the plus minus 2%. Yani there is a central value which has plus minus 2%. Yes? What central value will give you a maximum of 10%? Think. What central, yani true value will give you a maximum of 10%? 8. Yes? Your uncertainty is 2. Yani something x plus minus 2. So if maximum is equals to 10, if maximum is 10, so how much will be the x? X will be 8. Yes? Okay. So 8% is your decay. 8% is decay. So if decay is 8%, so remaining will be how much? 92%. Remaining will be 92. So 92, 100, e power. Lambda is negative log 2 over, you want in days? So years you will change into days. It's a good question. 5.27, 3000, so 365 into T. 192 divided by 100. Keep it. 0.5. Okay. Take natural log. Take natural log. So log of 92 over 100. Directly write 0.92 is negative ln 2 over 1923.55 t. Get the time t. Pretty significant here. 231 days. Activity 3.50 I did not use at all. I could use if I know the final activity. But they say maximum possible error of 10. So 8% I took. So 8% means 92 to 100 will be the ratio. Americium. UK, USA, America, Americium. Okay. 241 is artificially produced by a radioactive element that emits alpha particles. A sample of the americium of mass 5.1 microgram is found to have this activity. Wallah, it's easy. Can you do? Yalla, find mass. Alatul, the total mass divided by this. So, right, total mass how much? 5.1 micrograms. Yes? Over each how much? Alatul, 241 U. See? You became a Astura. 3.5. Then Nashir. 3.5 or it was 3.4 something. Yeah. So that's the problem, you know. I was going to round off wrong. Decay constant. Yalla. How do you do? Lambda is equals to 9 into 10 power 5 over 1.3 into 10 power Nashir. 4.37 you said. Half-life. Lambda you have, so half-life is log 2 over decay constant. Seconds. Yalla, years. Opa. Years. Seconds to minutes. Alatul hours. 3,600 for hours. 24 for days. 360 for years. 503 years. That's it. Another radioactive element has half-life approximately 4 hours. Compare the half-lives. Half-life 4 hours compared to 503. What does that mean? Decays much more. Which one will decay more? The first sample or new sample? New. So suggest why the measurements of the mass and activity of the sample of this element is not appropriate to determine its half-life. Yeah, it will decay much more during the measurements, so activity won't remain same. Yes or no? Sample? Will decay much more. Yes or no? While not much more, we are not comparing. Too much. While measurements are being taken. Thank you. I have done with you total all the March questions from 2003 till 10, all questions. Alhamdulillah, they are good questions. It means all the old and new questions have been solved with you.